Hello guys, today we're going to talk about reversible reactions and equilibrium. Now, we know that for any reaction, what happens is that products are formed from the reactants, but for reversible reactions, this is not just the case. The reactants are going to form the products, that's true, but products can also form the reactants. This is called a reversible reaction. It will be able to go both ways, forward from reactants to products, backward from products to reactants. For example, we have hydrated copper 2 sulfate. Hydrated copper 2 sulfate, this is a blue solid. It's formed of crystals. Its formula is CuSO4.5H2O. The dot means that the copper sulfate is chemically attached to the water. Upon heating the blue copper 2 sulfate, which is blue, it changes to white, which is the anhydrous copper 2 sulfate. The water is no longer attached to it, as you can see. It's separated from it. Because the forward reaction is endothermic, because copper sulfate, the hydrated one, in order to change it to the anhydrous copper 2 sulfate, we need to heat. We can safely say that when you add water to the copper sulfate, the reaction will be exothermic. Because, guys, for any reversible reaction, if one direction is endothermic, then the other direction must be exothermic. So, in a nutshell, hydrated copper 2 sulfate, which, as you can see, there's a dot here, upon heating, which is an endothermic reaction, gives me the anhydrous copper 2 sulfate, and the water is no longer attached to it. The reverse reaction, which is adding water to anhydrous copper 2 sulfate, must be an exothermic reaction, and it will produce the blue copper 2 sulfate. And this is called the chemical test of water, because if you have a solution which you're not sure of, if you add it to white copper 2 sulfate, then it will change to blue, verifying that water is present. Another chemical is cobalt 2 chloride. Cobalt 2 chloride hydrated crystals are pink. Upon heating, they change to blue, which is the anhydrous cobalt 2 chloride. Now, what will happen if you add water to cobalt 2 chloride, the anhydrous, the blue one? Can you guess? Yep, it will be an exothermic reaction, and pink crystals of cobalt chloride are going to be formed. These are the hydrated cobalt 2 chloride crystals. Now, I just want you to think, in the past reactions, did it happen at the same time that cobalt chloride and hydrated cobalt chloride changing to anhydrous, and at the same time the anhydrous cobalt 2 chloride change it to blue? Or was it one direction? First, you heated the cobalt 2 chloride in order to give you the products, and then you added water to the anhydrous cobalt 2 chloride to give you the reactant. This is called a reversible reaction. But the forward and the backward reaction, they happen at separate times, not necessarily at the same time. First forward and then backward, or vice versa. First backward and then forward. They don't happen simultaneously. Equilibrium is a different case. In equilibrium, both reactions take place at the same time. The forward reaction takes place at the same time as the backward reaction, until they keep on. One rate will decrease, the other will increase, until the rate of the forward and the backward reaction becomes equal. Naturally, this would mean that the concentration of the reactants and products are going to reach a constant concentration during equilibrium. Again, in the equilibrium, both reactions take place simultaneously, and both reactions take place simultaneously at the same rate. The concentrations of the reactants and products accordingly during equilibrium become unchanged, constant. Mind you, they are not equal. They are simply constant. The amount of moles of the reactant during equilibrium will be constant. The amount of moles of the product during equilibrium, again, will be constant. So we define equilibrium as a state where the rate of the forward reaction equals the rate of the backward reaction, and the concentrations of the reactants and products remain unchanged during equilibrium. For example, if you look at this reaction, the reaction between hydrogen and iodine to give you hydrogen iodide. This is the forward reaction. As it takes place, the backward reaction also takes place, which is the decomposition of hydrogen iodide into hydrogen and iodine. During equilibrium, we have the same rate, which means that at the same time, 1 mole of hydrogen reacts with 1 mole of iodine to give me 2 moles of hydrogen iodide at the same rate and at the same second. 2 moles of hydrogen iodide decompose to give me 1 mole of hydrogen and 1 mole of iodine. Now, if both reactions happen at the same rate, it is safe to assume that the concentrations will not change. Now, let us listen to what Le Chatelier said. There is a principle that the equilibrium will oppose any change that you exert on it. The position of equilibrium is going to shift, meaning, think of the equilibrium as a balanced seesaw. During equilibrium, it is in balance. Everyone is constant. Rate of the forward equal rate of the backward. But if you exert change that will cause a stress on one of them, then the equilibrium will oppose to change to go back to its original place. Now let's take it a little bit more into detail. But just let us remember that when we say exothermic, we mean that a reaction produces heat. When we say endothermic, we mean that the reaction takes in heat in order to proceed. What will happen if you exert change? What will happen if you change the temperature? Will the equilibrium take it? Absolutely not. Let us say for this reaction, this is an exothermic reaction. The forward reaction is exothermic. Now, if an exothermic reaction, it will produce heat. So if you increase the temperature, which means that if you increase temperature, an exothermic reaction will decrease in order to oppose it. This means that the backward reaction is going to work. The C and D will react to give me the A and B in order to try to absorb the temperature that you gave into the system. On the other hand, exothermic reaction, if you try to cool the system, the forward reaction is going to work, trying to produce heat in order to raise the temperature again. So in a nutshell, if the reactants and product is an exothermic reaction, then if you increase temperature, position of the equilibrium will shift left, trying to absorb the temperature supplied. If the reactant to product is exothermic and you decrease the temperature, then the forward reaction is going to work, increasing the amount of the product in order to supply the heat that you took by cooling. This is called opposing the change. That one of the reactions happens at a larger rate means that the position of equilibrium shifted towards this reaction. What we mean by that, if you heated this reaction and it is exothermic, and you find that the backward reaction is going to work more, this means that the position of equilibrium shifted towards the backward, and this means that heat will be absorbed in order to reach the balance again. Oppositely here, if you decrease temperature, naturally, the position of equilibrium is going to shift to producing more heat. How will the equilibrium produce more heat? It will shift its position forward, accordingly increasing the amount of the product and producing more heat to substitute the heat that you took in by cooling. A second factor is concentration. Remember, we said that the equilibrium is not going to stand still. It's going to oppose any change that you exert upon it. Therefore, if I have here the reaction at equilibrium and I add one of the reactants to the mixture, the equilibrium is going to try to decrease the amount of this reactant. How will it do that? It will shift forward. Shifting forward is going to decrease the amount of the reactants. It will produce more products. Granted, of course it will. Yet again, the equilibrium position is focused upon opposing the change. So it will shift the equilibrium forward and decrease the reactants. Oppositely, if you remove one of the reactants, the equilibrium is going to shift backward, shifts to the left. Why? To increase the concentration of the reactant that you removed. This will decrease the products and it will decrease the yield, granted. But again, the equilibrium is focused upon opposing the change. So it will shift backward in order to increase the concentration of the reactant that you removed. Now, remember when we talked about the pressure and the volume of gases and how by increasing the pressure, you decrease the volume, and how by increasing the volume, you decrease the pressure. Remember, we said that the pressure is formed by the collisions between the particles of the gas and the walls of the container. Increasing the collisions will increase the pressure. Decreasing the collisions will decrease the pressure. And this is why in gases, pressure and volume are opposite relationship. Increasing volume decreases the pressure and vice versa. This is important in order to think about what is going to happen if you have an equilibrium of gases and you exert pressure. Now I want you to count the number of moles of the reactants. In this reaction, I have 1 mole of nitrogen reacting with 3 moles of hydrogen to be in total 4 moles of gas. The 4 moles of gas of reactants produce 2 moles of gas in the product. Is this important? Absolutely. Now look at this container. Can you see the spaces between the particles? At a state of equilibrium, we have all three. We have nitrogen, we have hydrogen, we have ammonia, as seen from the particles, and here is the key. When you decrease the volume and you increase the pressure, the spaces between the particles decrease, which means the pressure is increasing. Accordingly, equilibrium is going to shift to smaller number of moles, trying to restore the spaces between the particles. Where is the smaller number of moles here? In the product. So therefore we say in this particular reaction, increasing pressure is going to shift the reaction into the side of smaller number of moles, which is forward. What if the smaller number of moles is going to be here? Then it doesn't make a difference. We're going to say it will shift backward. The important thing is that increasing pressure shifts equilibrium to smaller number of moles. So what do you think is going to happen if you decrease the pressure? It's going to shift to the side with larger number of moles. Again, let's wrap it up. If I have a reaction and the number of moles of gases is unequal on both sides, like here I have 2 moles of gases in the reactant, 1 mole of gas in the product. When this situation happens, changing the pressure is going to change the equilibrium position. Increasing pressure shifts equilibrium to the side of fewer number of moles. Decreasing pressure oppositely to the more number of moles. Remember, we said volume and pressure are opposite, right? Same here. Increasing the volume will favor the side with more number of moles. Decreasing the volume is going to favor the side with fewer number of moles, opposite to the pressure, as you can see. Now, let us think about the catalyst. By any means, catalyst will always, forever and ever increase the rate of the reaction. Is it specific to the rate of the forward or the rate of the backward? Absolutely not. Adding a catalyst will increase both rate of the forward and the backward reactions, which means that all that the catalyst is going to do is that it helps us reach a position of equilibrium faster, but the yield, no effect. The product concentration, no effect. So catalyst has no effect on the equilibrium position. Only effect is that it will reach equilibrium position faster, but it never shifts it towards forward nor backward reaction. In summary, in equilibrium, upon exerting change, it will oppose the change. If the concentration of the reactants increases, product formation is favored in order to decrease the concentration of the reactants. Oppositely, if the product concentration increases, then the equilibrium will shift backward in order to decrease this added concentration. For the pressure in gases and gases only, increasing pressure shifts equilibrium to the side of smaller number of moles, which is the forward in this reaction. Decreasing pressure shifts equilibrium backward to the size of larger number of moles in this reaction. What about temperature? For temperature, increasing temperature favors the endothermic direction because it is opposite to the change that you exerted. Remember that. Decreasing temperature favors exothermic direction to oppose the change and produce heat instead of the one that you took when you cooled. And remember, last but not least, if one direction is exothermic, the other must be endothermic. I hope this was beneficial to you guys and it will help you understand more how equilibrium works.